Hey guys, and welcome back to this video on the Science and Motion Lab, Motion of a Falling Marble. Now, depending on what your teacher has assigned you, this video is kind of meant as a backup, essentially in case you've gotten stuck and you're unable to do the lab or just figure it out on your own. Your teacher may have assigned you the whole lab, which is like almost 16 pages, or they may have shortened it down. Either way, this video is just meant to kind of help you with some of these first calculations and how to do and linearize through the graphs. And if that word linearize just scared you, then this video is definitely for you. So essentially, you were supposed to have either done the lab in class, or your teacher did the lab as a demo, or you watched the virtual data lab that we did as Science in Motion, and you gathered some data from it. So this is some data that I took a little while ago in my office. And so it's going to give me something, and you can use your data and kind of go along with it. So here's the thing. All we were doing in the lab is we could have done this lab without such high-tech equipment. We could have went outside, and you could have found really high objects to drop things off of. Well, that's a little bit dangerous, though, because you could fall off those objects. So all we were looking at is the distance and the time, comparing it for objects falling. So anyway, let's kind of go on. You have a second data table. So the first data table you should have been able to do pretty easily, because all it was write it down in centimeters, write your meters, then write the time down. Now, the other data table looked similar to this. You were supposed to go through and find some velocities. And so essentially, how is it that you find a velocity? Well, think about it. You had distance and time, and you've already done a lab, motion of a toy car, where you've already looked at these factors of distance and time. So what I'm going to do is this. I'm going to do most of the lab inside of a Google Sheet, and that's going to make my calculations a whole lot easier. So the first thing I'm going to do is this. I'm going to write a column. I'm just going to call it velocity. I'll come back and change that in a second. I'll say velocity in meters per second. And this is what I like doing in a Google Sheet. We can now, if you've put your data into a Google Sheet, you can come over here and just type in the equation. So I want distance divided by time. So for me, that is cell B2, and B2 divided by cell C2. Boom, equals, and so see, I got it. Now all I got to do is take this, and I can copy that equation all the way down. So now I've got these velocities calculated. So like my first one's 1.15, or if I'm doing sig figs, it'd be like 1.1. But now let's go back and look at that for a second. So let's answer this question, 1.1. If you've taken and done nothing but distance divided by time, what kind of velocity is that? Is that an instantaneous velocity, or is that an average velocity? Well, remember, the distance in instantaneous velocity is, if we were in calculus, we'd probably write the expression dt, as in we would be meaning instantaneous velocity is very small time periods. Now, you may be looking at this going, Mr. Cole, 0.2 seconds is pretty small. So when you say small, what do you mean? I mean, for instantaneous, I mean like 0.000. I'm talking super instantaneous. The actual science word is infinitesimally small. So I'm trying to lead you to the point that what you have calculated is actually an average velocity. So this list of velocities that we have, that I've just calculated in my table, and hopefully you're doing the same, those are average velocities. So now then the question, again, you're supposed to have already tried this on your own. This is the backup. All right, Mr. Cole, I've got stuck, so that's why I'm watching this video. So now the question really boils down to this. And what we're having to do is this. Remember, this marble was up at the top, and let's think about kind of what took place here. The marble took place, the marble falls. And so let's see what we can do. So here we go, and let's kind of look at this. What I really wanted to know is this. I really wanted to know, what is this final velocity down at the bottom? Well, let's do something real quick. what's the initial velocity up at the top? Well, if you remember the little picture of that bracket of mine, the marble was just kind of sitting there. So we know that the initial velocity was basically 0, right? So the question then becomes, what is this final velocity? Now, like for this first one. So like for my very first one up here, if you think about it, you've just found the average velocity for the first one. For me, in my example, was 1.1. So as I look at this, now my question to you would now be pretty simple. What is 1.1 the average of? 0 and what other number? Remember, another way to look at an average is all you're doing is adding two things together and dividing by 2. So if you're trying to figure out what the final velocity is, well, think about it. The average of 0 and what number makes 1.1? Oh, well, that's pretty easy. That's 2.2. So essentially, all I'm going to do is times my averages by 2, and that's going to give me these final velocities for this last column. Now, the only catch I might add to this, because somebody will think, well, from now on, I can just times average velocities by 2 to get final velocity. That's not true. The only reason why that worked this time is because the initial velocity is 0. Now, as long as your initial is 0, then yeah, you can kind of pull that little trick. So you're good to go there. So now I'm going to do something. I'm going to type, let's see, a column. I'm going to call it final velocity in my Google Sheet, except I'm going to misspell velocity. Wow, that's terrible. Velocity. There we go. Finally. Hey, see, don't it make you feel good? See somebody else mess up? Final velocity. And now let's type an equation for that. So all I'm going to do is I'm going to take cell D2, use an asterisk if you're not used to like doing spreadsheets, times 2. Boom. Hit enter on my keyboard, and now look at this. Drag that down, and now I have calculated all the data that I need for my lab. Essentially what this video is going to help you do is there's kind of like the main elements of this lab. Three of your main elements are these graphs. So let's do something. Give me like a little extra sheet here that I can work on off to the side. So what you're going to look at, one of the first assignments in the lab, you're going to try and make a graph of velocity final versus time. And then when you do that, you're going to do a 4-step analysis on that video. Now, again, if the teacher is intent on you figuring all this out by yourself, then you probably shouldn't be watching this video. So this is your last case, I'm stuck, help me finish video. So now let's kind of go through then and take a look and make that graph. So let's go back to Google and get in there and let's do something. I'm going to click off over here to the side because I've got a lot of data. So I'm going to go up, insert, chart, and it's no data, and I'm going to go tell it what kind of chart I want. I would like a scatter plot, please, Google. So do scatter, and now it's going to ask me, well, what do you want to graph? So for my data range, I'm going to do this. For data, I want to graph a final velocity, except for the fact that I'm kind of messed up now because all this is in the way. Cancel, get out of the way. There. Let's try it one more time. For my data range, I'm going to do this column of final velocity. So there's going to be my data range. And I've got that graph, but here's the thing. It's not graphed against anything, so it doesn't make a lot of sense. So I'm going to go here and click Add X-Axis. And now I want to do a graph of velocity versus, I want time to be this other column. Okay. And so I've got my graph, and it's not super beautiful, but it's not terrible. So let's do something. I'm going to go ahead and start customizing this graph. I want to give it a title. So vertical, let's see, title text. Let's call this velocity. Wow, my keyboard stopped working. Velocity final versus time graph. So let's give us a name. And so, wow, that is actually not what I wanted though. So let's go to chart title. And that's the one I want to actually say velocity final versus time. There we go. Now for my horizontal axis, I'm going to do something. I'm going to type for it I'm going to type time. Now I'm also going to put the unit in there. So time in seconds. And now let's fix that vertical axis, okay? Let's do this. We want velocity final or final velocity. It doesn't matter how you put it, but it's going to be in meters per second. So let's do that. And that kind of gets a little bit glossed up. So now we've got a little better graph in terms of displaying for, you know, our teacher in class. And let's do something else. I'm going to do something. Go down to where it says series and add your trend line. And so my data doesn't look too bad. It's looks pretty linear when we add the line to it. And now where it says label, I'm going to do something. Use equation. And so I've got an equation up here. So we've got final velocity equals. See if I can copy this data down real quick. Oh, come on. There we go. Copy. So my graph essentially, let's see if we can bring this over and let's look at it in like a little bit of detail somewhere. So when I look at this graph, and this is the part where we're going to do a 4-step on this. So if you think about it, that 9.8, that represents the slope of my line. And this, of course, is my intercept. So let's do the 4 steps. So we ended up with a nice linear line. Step number 1, write down the equation for a straight line. Well, that's easy. Y equals mx plus b. Check. Got that, Mr. Cole. Step number 2, in place of y, write down your variable. Okay, well, that was velocity final. M, in place of x, write your variable there, t plus b. All right, so far, that's very easy. You got this. Step number 3, substitute in your value from your graph. So don't use mine, but use your value from your graph. So mine is 9.8. And now I need a unit. Remember, that was one of the problems we said. When you're doing it in Chrome, if you were using like Logger Pro like we normally do in lab, it'd be better because it kind of would spell out your unit. So let's do something. What is the unit for velocity? The unit for velocity is meters per second. What is the unit for time? Seconds. So you've got rise over run, meters per second, which is the same thing as a meter per second square. So we've got meter per second square times time, in this case plus or minus, it does not matter how the data comes out, 4.79 times 10 to the negative 4. And the unit would be a meter per second because that is our intercept of our y-axis units. So I'm going to go ahead and do something. I'm going to call that very easily a 0 because to the negative 4th is definitely less than 5%. Remember, that's the rule we've always set. If your intercept is less than 5% of your maximum value on your y-axis, we'll call it 0. So now the only thing left is step number 4. And in step number 4, we're looking at this and we're trying to figure out exactly what does this 9.8 represent in here. So we're going to write a general equation for this line. So VF is equal to, now you can either use the number or you can use the unit to help you figure this out. So as you're trying to figure this out, you may have to go, well, what is a meter per second square a unit for? Well, think about it. This is how fast, that's why I like saying meter per second, old school. Because you're saying this is how fast it took me to change speed. It's the speed of your speed. Wait a minute, I feel a physics definition coming on. It's the rate of change. Oh, let's throw an E in there. Change in velocity. Oh, wait a minute. Go look that up in your physics textbook. It's got a name. That's what we call acceleration. Now, the 9.8 should stand out because that is the Earth's gravitational acceleration that something falls at. So 9.8 is kind of like a famous number in physics. You can tell I use kind of generated data because usually you don't, when you're taking real data, you usually don't get like these perfect numbers like this. I think if you use the data in the virtual lab, I think it comes out to like 9.5, something like that, if you do everything correctly. Now, here's the thing. In your physics lab book, you will see an equation that looks close to this. In your physics lab or in your physics book, you'll notice an equation that looks like this. And it's just your velocity acceleration equation. And you should be looking, going, wow, we basically derived that by doing a graph, but how come we didn't have a velocity initial? And this is where now I would take you back up to your intercept. Look at your unit. It's a meter per second, which is the unit for a velocity. It's just in our case, what was our initial velocity? It was 0. So now we can come in here and we kind of see where this equation comes from. So I'm going to shut this video off here, and I'll make another one in case you get stuck on your linearizing equation. So anyway, I hope this helps you out, and I'll see you in the next video. Bye.